Space, the final frontier. This is the Observer's Notebook, the official podcast of the Association of Lunar and Planetary Observers. Its mission to explore the solar system, to seek out new observations and data, to boldly go where no podcast has gone before. And now the host of the Observer's Notebook, Tim Robertson.
Hello and welcome to episode 190 of the Observer's Notebook, the official podcast of the Association of Lunar and Planetary Observers. I'm Tim Robertson, the host of the Observer's Notebook and also the coordinator of the training program within the ALPO. Thank you for downloading and listening. The Association of Lunar and Planetary Observers collects and analyzes observations of various solar system bodies and associated phenomenon, and publishes detailed reports concerning these bodies in its quarterly publication, the Journal of the Association of Lunar and Planetary Observers. This podcast depends on donations from you, our listeners, to keep it going. If you enjoy what you hear on the podcast, you can donate to it via Patreon. You can start off by giving as little as $1 a month. If you feel even more generous, for $5, you receive early access to the podcast before it goes public. For a monthly donation of $10, you receive a copy of the Novice Observer's Handbook. And for $35 a month, you receive producer credits on the podcast. You can find out more by going to www.patreon.com/observersnotebook. And if you'd like to join the ALPO, membership begins at only $22 a year. For more information, find us at www.alpo-astronomy.org. And you can also find us on Facebook. Just search for ALPO Astronomy. And this podcast also has a Facebook page as well. Just search for Observer's Notebook. And if you enjoy what you hear in the podcast, please subscribe. That way you'll never miss another episode. And now we're going to get the latest from the OSIRIS-REx mission to the asteroid of Bennu. Enjoy. All right, I'd like to welcome everybody back to this edition of the Observer's Notebook podcast. And today we have a very special guest, Tom Zega. He was the science officer or something on the OSIRIS-REx mission. How you doing, Tom?
Good. Thanks, Tim, for having me.
Yeah. So what is your title on the mission?
I guess there's multiple titles. So I'm a science team member,
okay.
I guess, first and foremost. And also I am a lead of the mineralogy and petrology working group. So the science team is divided up into different groups based on people's scientific expertise. My expertise falls into the study of mineralogy. And so I lead a group of other scientists that share that kind of expertise. And our job is to sort out the minerals, their compositions, their abundances, and how those contribute to the overall rock type in the sample return from asteroid Bennu.
Oh, very good. Very good. Now, you graduated from the University of Arizona State?
I graduated from, I did my doctorate at Arizona State University. I finished there in 2003.
Okay. So why don't you give our listeners that don't know a little bit of background about the OSIRIS-REx mission?
Yeah, sure. So the OSIRIS-REx mission headed to asteroid Bennu. It was launched in 2016. There were good reasons why OSIRIS-REx chose to go to asteroid Bennu. Among the many reasons were that it is an asteroid that is rich in carbon. Carbon obviously is an element that's essential for life. And so one of the driving motivations to go to do a sample return mission was to learn about the building blocks of life, the precursor molecules that may have been delivered to the early Earth. Asteroid Bennu was also selected because it's among one of the most hazardous asteroids. It has a chance, very, very small chance. So I don't want your audience to get worried too much about it, but a very small chance, something like 1 in 2,700 chance of hitting the Earth at some point in the future. And so going to the asteroid, inserting into orbit around it, doing a series of measurements, including high resolution imaging, measuring its chemical makeup, measuring its size, getting some sense about its orbit and rotation, would help inform us about the chances, however unlikely, that it could have an actual Earth crossing orbit at some point into the future. So those were among the reasons that asteroid Bennu was chosen. And as I said, it launched in 2016. It rendezvoused and touched down on the asteroid. It was, I believe, in October of 2020. And then we returned sample from Bennu in September of this past year, September 23.
Now, how long have you been on the mission?
I've been on the mission in one form or another for many years. So the first 5 years or so of the mission, I had the status of collaborator, mostly because that phase of the mission is a lot of engineering, a lot of planning. There isn't any sample science during that phase of the mission. And my role started to increase after the orbital phase of the mission was winding down. We had done lots of remote sensing. We had a good idea of what the surface of the asteroid looked like, what it was composed of. And then we did tag. And then it was time to start thinking about, okay, samples are coming back. And so it's interesting how the missions like this work. The science team almost completely turns over, not entirely, but almost completely from folks that are focused on getting the spacecraft off of Earth, getting it into orbit around the asteroid, doing lots of high resolution imaging and spectroscopy, to sample scientists now who are concerned about actually measuring the sample when it gets back to Earth. And so my role increased basically from around 2018 or so till the present day, where I'm heavily involved.
Okay. Now, you mentioned going into orbit around an asteroid. That's not an easy thing to do, is it?
No, it's not. We have an excellent flight dynamics team between Goddard Space Flight Center and Lockheed Martin, the corporate partner on the mission. And there's lots of folks who it's basically their job to understand the hazards of the asteroid and how to get a spacecraft the size of OSIRIS-REx to orbit around a body as small as Bennu. It's about 500 meters across, so it doesn't have a lot of gravity, but it's the job of these folks to figure out how exactly to do that. And they did it. They did it with flying colors.
Yes, they did. It was pretty amazing. Yeah, though I remember watching the thing live on the internet. It was pretty interesting to see that.
Absolutely.
Now, how large of a sample has it returned from the asteroid?
So the official mass that came back from Bennu is 121.6 grams. So it's basically enough to fill a coffee cup.
Oh my. So it's enough to share with a bunch of scientists, huh?
Yeah, it's interesting you say that. So I get different responses when I'm asked that question. Some people will say, "Oh, that's not a lot of material." Other people will say, "Oh, that's plenty of material to share with the world." And I think your reaction was probably the one that's consistent with mine. It is a lot of material, especially with some of the tools that we can bring to bear on understanding the composition and mineralogical makeup of the sample. We have tools that are fully capable of interrogating the materials within the return sample down to the atomic level. So we can work with very, very small masses on the order of picograms if we need to. So 121.6 grams is a lot of material.
It is. Yeah. So you've personally examined the samples, I assume, since I've been back?
Yes. Yeah, we have quite a bit of sample in our lab, which is just a few doors down from where I'm actually sitting as we're talking.
Okay. So what was the initial excitement? What was the initial feeling when you first cracked open, when you finally got the module cracked open where you could actually see the samples inside?
It was actually the whole week was interesting. So I was also part of the what's called the Quick Look team. I wasn't on the recovery team. So the recovery team was the group of people on the science team, a select group of people that went out to Utah and actually waited for the sample return capsule to land. And if you were watching the NASA TV feed that day, you saw it come down, you saw the parachute deploy. It's that sort of candy cane colored parachute that deployed, and it made a beautifully soft and picture perfect landing in the Utah test range. So that was on Sunday. I believe it was, if I'm not mistaken, was it Sunday the 24th? And then Monday the 25th, it was flown out to Johnson Space Center. Yes, Monday the 25th, it was flown out to Johnson Space Center. I was actually home that morning, Sunday, watching it on NASA TV, like many other people, because I was getting on an airplane in just a couple hours to go to Houston to await its arrival. So I got there on Sunday and was ready for it with a group of other people on the Quick Look team to receive it on Monday. And so there was lots of anticipation for its arrival on Monday. We assembled at Johnson Space Center outside the Building 31, where the sample is curated, and we greeted the recovery team as they came back to Johnson, because they flew from UTTR to Ellington Air Force Base. I believe it was on a C-130, and then they drove the capsule with a police escort directly to Johnson Space Center, where we were all waiting for it. It wasn't clear if we were going to get our hands on it on the sample on Monday, but by the time they arrived with everything on site, it was already in the afternoon. People were really tired because they had been up for many, many hours preparing and waiting for the sample. So a decision was made to hold off on doing any kind of sample activities that day. And so we convened the next day, which was Tuesday, as a science team. The sample return capsule was already upstairs on the second floor of Building 31 at JSC in the clean room there, and the curators were ready to go. And the science team, including myself and a group of others, as well as Lockheed Martin executives, were sitting on the floor below in the conference room there, watching the curators work on the sample return capsule on a video feed, because the clean room it's not that big. It can't accommodate everyone. You wouldn't want everyone in there anyway. So that's how we were seeing it, including Dante Loretto, who's the PI of the mission. And so you can imagine both the excitement and the anxiety, I guess, the nerves in the room, in the conference room that morning. You know, everybody was excited before we got started, but once we got started, you know, the room quieted down. I think lots of people were on the edge of their seat waiting for the curators to just open the lid of the SRC, because you've probably seen it. It looks like a clamshell.
Right.
So, you know, they had to loosen up the fasteners in order to get the clamshell open. Once they open the clamshell, then we have access to what's called the avionics deck, and the touch and go sample acquisition mechanism, or TAGSAM, the thing that looks like if you remember old cars, especially those from the muscle era of the 60s and 70s, they all had carburetors on them, right? Before fuel injection. And so the TAGSAM looks like one of these old style carburetors, and that's what actually touched down on the asteroid. Nitrogen was purged through it, and then it disturbed the regolith, and then the regolith was forced through the carburetor and trapped inside of it, or this carburetor-like TAGSAM device, and trapped inside of it. And so you can see, once the SRC clamshell opens up, you can see the TAGSAM there on the avionics deck. And so opening that was the first really important step to telling whether or not we had material inside of the TAGSAM, because we expected the avionics deck would probably be coated in fine grain dust of Bennu dust, whatever it looked like, because we didn't know at that point until we opened it up. Was it going to be dark dust? Was it going to be some other color to it or contrast to it? We didn't know. So the lid opened up, and I think we were all probably leaning on the edges of our seat. I was sitting on one side of the room. Dante, who's the PI, was sitting really close to the TV screen and looking at the video feed. I think one of the Lockheed Martin execs was just next to him. And as they opened it up, he was looking really closely, and he was seeing things right away that I couldn't see from my vantage point. So my reaction was like, is there anything there? I can't tell. And he's looking, and I hear him say, there's a lot of material there. There's a lot of material on the avionics deck. And as your eyes became trained to the picture on the TV screen, and if you could get up close to it, then you could see what he was seeing. And he was completely right. There was all of this black, fine-grained dust on the outside of the TAGSAM sitting on the avionics deck. And it was at that moment that we knew the TAGSAM must be full of material. And I think there was like a proverbial sigh of relief in the room when that happened.
I'm sure. Yeah, that had to be pretty exciting for you.
Super, super exciting. And as the next day or two went on, there were higher resolution photographs taken of that avionics deck, and we started seeing different grain sizes. We thought we were seeing maybe even different material types. So, there was temptation to start interpreting what was in the sample. I myself was even guilty of that. But, it was all in the spirit of excitement and, eagerness to start doing some really fun science.
Now, was there anything that surprised you when you personally initially started examining the samples?
Yeah. For me, honestly, it was how black the sample was. So those of us that do this for a living, like a lot of us have been doing this for decades. I myself have been doing this now for 25 years. So I've worked on carbonaceous meteorites that are analogous to the material that we brought back from the surface of asteroid Bennu. So, based on decades of experience, mine and many others on the science team, we sort of had a mental picture of what the makeup of this surface material might actually be. But it was also based on the images we had collected during the encounter and orbital insertion phase of the mission and the spectroscopy that was acquired. So we had some sense of what might actually be there. We expected it to be rich in organic compounds. We expected it to be rich in hydrated silicates, carbonates, things of this nature. But I don't think I expected it to be as black as it turned out to be. Like, it was so dark. It looked like, I don't know if you've ever seen like carbon black. It's this material they use as like a pigment in different types of materials, including things like paint. Like it was so dark that I think it really surprised all of us pleasantly, not in a bad way. It became even more curious after we saw how dark it was, this material that came back. So I think that was one of the first major surprises. Another one was how fine grained it was. So based on the orbital phase of the mission, we saw things on the surface, literally boulders. So if you go back and you look at some of the earlier images from the mission, you see these large scale boulders on the surface. Some of them look like they had these bright carbonate veins running through them. So not seeing that stuff right away was also one of the big surprises. And so we're working all of these things out now and trying to reconcile what we see in the sample at the micrometer scale with what we were seeing at the sort of meter to kilometer scale during the orbital phase of the mission.
Okay, then other than your visual observations, what about organically? The physical makeup of Bennu. Has anything surprised you on that? Or you pretty much had it figured out before?
I wouldn't say we had it figured out. I think we made some good educated guesses as to what might be in the return sample based on what we were seeing in images from orbit and from the spectroscopy data. There has been a big surprise, and I think this was reported during the press conference, a phosphate phase in the sample that early days we didn't know what it was. We thought maybe it was contamination. But we've since confirmed that it's actually indigenous to the sample itself, and it has a quite interesting and possibly exotic composition to it. And so that's actively being studied.
Interesting. Wow.
Now, the organics. Sorry, go ahead.
No, go on.
The organics themselves, right? So there's still a lot to uncover with the organics, and I'm not an organic chemist, so I'm not maybe the best person to ask about it. We have been looking at things like the amino acid content, the abundance of those materials. There's a whole working group that's just devoted to organic sample analysis. But we have come across some things in the sample that are organic. They're not amino acids; they are organic, but they're things that are like macromolecular polymer type structures, which we've seen before also in carbonaceous meteorites. And so it's clear that there are some similarities between the returned surface material from asteroid Bennu and carbonaceous chondrite meteorites that are already in our sample collections. The important thing to keep in mind about meteorites, of course, is that we don't know where they come from. So we're generally at the mercy with meteorites. People, those of us who study meteorites, we're at the mercy of what falls from the sky, right? Unlike geologists who can go out and actually sample a rock outcropping, look at the context of everything around the sample that they might be taking from it. If you do this kind of work, cosmochemistry, you study meteorites, you don't have that luxury, right? I can't get into my Battlestar Galactica or my Starship Enterprise, fly out to the asteroid belt and grab a sample of any asteroid that I would like. I would love to be able to do that, but I can't do that yet, right? So OSIRIS-REx and its sort of sister mission, Hayabusa 2, and 1 for that matter, were the first missions to actually go and grab pieces of asteroids and bring them back to Earth, so that we actually have all of that context for the sample that we've acquired from the surface of the asteroid. And so it's interesting to see now that the decades of research that the scientific community has done on meteorites is showing some similarities between the meteorites themselves and specific asteroids that we've gone and visited now out in space.
Yeah, the interesting thing is, though, with the asteroid sample missions, you're getting a pristine sample of a space rock. When it's coming into the Earth as a meteorite, the atmosphere of the Earth probably has some effects to it as well.
Yeah, that's a good point, right? So one of the reasons, obviously, to go and get a sample is to keep it as pristine as possible. And certainly the science team and the curation team have gone to great lengths to do just that with the OSIRIS-REx samples. Yeah, you're right. So when meteorites fall on Earth, they're classified into one of two types, either falls or finds. So a fall is a meteorite that somebody actually witnesses coming through the atmosphere, and it's collected very shortly after it falls, so that it hasn't experienced much in the way of terrestrial weathering, whether that's rain or snow, or it falls into a lake or an ice sheet, or wind erosion, et cetera, et cetera. So those of us that study meteorites and are interested in the chemistry of the early solar system tend to go and request samples that are falls rather than finds. Finds, in comparison, somebody might be walking along some part of the Earth where a meteorite might have fallen at some point in the past. It could have been recent. It could have been 100 years ago or more. And they come across this rock. They find it. It looks exotic. It gets tested. Turns out to be a meteorite. But we don't know how long necessarily it's been on Earth unless we do some sophisticated types of measurements on it. And the meteorites that are classified as finds, of course, they have been sitting around on the surface for a while, and they certainly can be weathered and altered, and they are not pristine, unlike their counterparts, the falls, and certainly unlike a sample return from an asteroid with one of these robotic spacecraft missions, for sure.
True. Now, you've analyzed samples from other missions to asteroids, correct?
Yeah, so I was involved, or I'm still involved, in the Hayabusa 2 mission to asteroid Ryugu, and I was involved in, or I had samples, I still have samples of asteroid Itokawa that was returned by JAXA's Hayabusa 1 mission. That's right.
Now, are you seeing differences in anything between all these samples that make them different types of asteroids?
Yeah, so among the 3 different sample return missions from asteroids, there are differences between certainly Itokawa and Ryugu and Itokawa and Bennu. So Itokawa is a very different type of material than that return from Ryugu or Bennu. So Itokawa is not a carbonaceous rich asteroid. So its mineralogic properties and makeup look very different from those returned from asteroid Ryugu or asteroid Bennu, which are carbonaceous asteroids, right? So Itokawa is it's composed of potassium and calcium rich silicates, magnesium and iron rich silicates. It doesn't really have much in the way of hydrated silicates. We recently reported some results where we found the mineral halite, which is, as most people know it as common table salt. We found halite in asteroid Itokawa samples, which suggests that there was water present at some point on Itokawa, but it wouldn't be at the same levels or abundances that we see it in the sample returned from asteroid Ryugu or the sample returned from asteroid Bennu. When we look at asteroid Ryugu, we look at asteroid Bennu, these samples are chock full of minerals that form by reaction with liquid water. There's no ifs, ands, or buts about it. Chock full of minerals that form by reaction with liquid water, as compared to Itokawa, which was relatively dry. There may have been some water around, but it looks to have been relatively dry. So very distinct types of geologic activity occurring on these different asteroids. When we compare Bennu to Ryugu, actually there are quite a few similarities between the mineralogic makeup of these 2 asteroids. They're carbonaceous, they're fine grained, they're very dark in color. They have abundant sheet silicates, carbonates, sulfides, and other minerals that are characteristic of, like I said, reaction with liquid water. There may be subtle differences in the types of chemistry that occurred on these different asteroids, maybe some subtle differences as to what pressure and temperature conditions prevailed during reactions, liquid water reactions, but that's all being worked out right now as part of the research on these samples.
So to be created in an environment with water, where do you think that came from? I mean, the asteroids themselves, what is the origin?
Yeah, so another great question that the science teams are trying to get a sense of, right? Where did these asteroids come from? B, where did their water come from? And C, did any of that end up, in any of that water in some way being delivered to the early Earth, right? Because Earth is chock full of water, right? So, to answer the first question, we don't entirely know. So, when planetary scientists talk about asteroids, they often use the phrase parent body, right? What was the parent body? Okay. Did the asteroid that we see right now that we call Bennu, did it form that way billions of years ago when the solar system was being put together, or was it part of some other body, some larger body that we just don't have access to at this point, right? And we're trying to work that out by looking at the properties of the return sample, its chemical composition, its mineralogical makeup, its isotopic composition, even things as large as the orbits of these things, their trajectories, what type of asteroid families, because asteroids are grouped into families based on their spectroscopic characteristics. So what asteroid family might Bennu have originated from? And if so, is there any way to reconstruct its original parent body? So that's an active work in progress. As to the water itself, obviously we know water or hydrogen was very abundant in the early solar system. When you look at the current architecture of the solar system, we can divide it between the terrestrial planets, right, which are Mercury, Venus, Earth, and Mars, and separate that from the gas giants, which are the outer planets, which are chock full hydrogen and other very interesting elements and molecules, right? So there was plenty of hydrogen and even oxygen around the solar system to make water. Okay, the prevailing hypothesis as to how these asteroids got their water is that they accreted at some distance away from the sun where water was stable in solid form, i.e., as ice. And that ice accreted together with all the other dusty material that made up the original parent body of the asteroid, in this case, Bennu. And that heat, either produced from the accretion process itself or the in situ decay of radioactive material, drove that ice to become liquid. In other words, the in situ decay of radioactive nuclides provided enough heat to melt ice and start driving hydrothermal reactions. So we, in a very real sense, we think that liquid water was probably stable, if not at the surface, at least in the interiors of the asteroid itself, allowing reactions between the solid rock and the water to produce the secondary minerals that we see in the form of things like carbonates, water-bearing silicates, sulfide grains, magnetite, which is iron oxide, and other types of materials that we know from terrestrial geology, from studies in the laboratory, that these things form through reaction with liquid water.
Wow, that's pretty fascinating. Huh. So
yeah, it's really mind-boggling to think that, you know, not just planets like Earth, right? Earth obviously has a very active hydrological cycle. We understand it very well. We think Mars probably had such a cycle at one point. Mercury is very dry. Venus is very hot. But the idea that asteroids themselves could have had, right, these are much smaller bodies, right? Bennu is something like 500 meters across, could have had active hydrothermal systems is really, really fascinating. It's really interesting to think that that such small bodies could have had active hydrothermal systems, possibly much like that. Some of the hydrothermal systems that we find on Earth.
Wow. Now, like most science missions, for every question you answer, you get 15 more questions. And so what are some of the things that you're working on now to further your knowledge of Bennu and our solar system?
Yeah, great question, right? So, of course, new questions come up every day as you learn new things about the sample. But, you know, one of the big questions in early solar system chemistry and planet formation is trying to understand how material moved around in our early solar nebula. So the solar nebula it's this phrase that we use to describe this cloud of gas and dust from which the sun and planets form, right? And when we think about the solar nebula, we think that based on dynamic studies, but also, to be frank, sample return missions, we think that there was large-scale radial transport in this disk of dusty material of gas and dust. So the Stardust mission, which returned samples from Comet 81P, Build 2, back in the early 2000s, showed us that some of that material contained minerals rich in calcium and aluminum oxides and calcium and aluminum silicate materials. So these things, there's a name for these things that we find in meteorites. They're called calcium and aluminum rich inclusions, or CAIs. Scientists love acronyms, so we tend to use these a lot. So these CAIs, we find them in certain types of meteorites. They've been radiometric age dated to 4.567 billion years old. So these mineral assemblages, these CI mineral assemblages, are basically what anchor the timestamp of 0 for solar system chronology. Okay. So time 0 starts with the age dates of these CAIs. These things, these objects, are very, very refractory, meaning they have very high melting points. We know their thermodynamics pretty well. And our models, thermodynamics and our dynamic models, tell us that they formed very close to the early sun, probably well within the orbit of, inside the orbit of Earth. So we're 1 astronomical unit away from the sun right now. That's where Earth sits, right? So we think these CAIs probably formed well within 1 astronomical unit. Now, the fact that we found them in the Stardust sample implies that they were transported. These objects may have been transported over very large distances, because comets form way out in the outer solar system. And the reason why we're interested in comets is because they're potentially time capsules of those very early stages, because they spend so much time in the outer solar system. They're very cold. If there's any water in it, it's probably icy. All that stuff is probably very well preserved, right? So the fact is that we found this stuff in Comet 81P, Vil2, suggests that these materials that form very close to the sun were probably ejected and transported over many, many tens of astronomical units to the outer solar system, implying that the solar system itself was maybe convective. There was large-scale radial mixing inside of it, okay? So that, as an overarching theme or context, we try to place the stuff that we see in meteorites, and of course now in the return sample, into that context. So, among the things we're asking ourselves when we see the sample, do we see any of these objects like these calcium and aluminum-rich inclusions? Do we see other things like chondrules? So chondrules are these glassy silicate spheres that define chondrites, chondritic meteorites. Do we see any chondrules? We think those also formed at very high temperatures, maybe 1 million to 3 million years after the CAIs did, through some sort of flash heating process that melted them, forming their very rounded, compact structures. Do we see any other things that we know formed during the early stages of the solar system, and or might imply large-scale mixing events in the early solar system? So these are among the questions that we're asking ourselves as we go through the sample and try to unravel processes that we know or we're almost certain happen in situ on the asteroid itself by reactions between solids and liquid water, versus those that may have happened well before the asteroid accreted by minerals condensing out of the gas phase somewhere close to the early sun. So there's a lot of history, there's a lot of chemistry that occurred over huge spatial scales and at different periods of time that we're trying to work out now from looking at the return sample.
Okay. Now, who are some of your scientific partners that are analyzing the samples?
So the science team spread all over the world. In the United States, there's obviously the group here at the University of Arizona, where I am at. There's a big group at Johnson Space Center, NASA Johnson Space Center in Houston, Texas. There's a group in California. Colorado is another group. Smithsonian Institution, Purdue University in the U.S., and I might be forgetting some. We've got colleagues in Canada, Japan, Europe, the UK, so all over the world.
Okay. Now, are there any other asteroid sample return missions on the books?
Right now, there's not another asteroid sample return mission that I'm aware of, either within NASA or JAXA. JAXA is planning a mission to go to the moons of Mars and bring back samples in the next few years.
Okay.
And I'm sure you've heard about Mars sample return missions. So that may be on the horizon. I don't really know the status of MSR.
Last I heard, it wasn't good.
Yeah, at the moment, based on the cost of returning a sample. But the truth of it all is now, Tim, that we know how to do this, right? We have the architecture, we have the engineering, we have the science down pat. We've shown that we can do this. I think subsequent missions, if NASA or someone else wanted to support such a mission, the template's there, and we could probably do it for less cost next time around. And if you ask me scientifically, there's more than enough targets and more than enough scientific justification to go to lots of these different asteroids. bring back samples and look at them, with some of the most sophisticated analytical techniques that we have on the planet here.
Yeah, very good. So what's some of the instrumentation you're currently using at your lab?
Yeah, so here at the University of Arizona, we have electron and ion beam microscopes. So what our focus is here is looking at mostly the inorganic components in the sample, although we look at the organic components too. But what we do is spatially resolved microanalysis. So we're interested in understanding what minerals are there, what is their composition, their chemical makeup, their stoichiometry, right, their chemical formulae. Mm-hmm. What are their atomic scale structures? What minerals are they spatially associated with? And then what does that tell us about how they form? So what kinds of chemical reactions led to their formation? Under what conditions did those chemical reactions occur? And all of that information is gleaned by understanding what's there. And to understand what is there, you need instrumentation that's capable of actually measuring these really, really fine grain materials. And so we have ion beam microscopes that allow us to actually look at the isotopic composition. So we have something called a nanoscale secondary ion mass spectrometer that allows us to measure the isotopic composition or trace element composition of the minerals within the sample. We have scanning electron microscopes. So scanning electron microscopes allow us to look at the textures in the sample down to the nanoscale. We can look at the mineral compositions. We can get very high resolution images of the surface and look at things like spatial relationship and context. We have something called an electron microprobe. So an electron microprobe works sort of like a scanning electron microscope. That is, it can take very high resolution images, but it can also tell us what the chemical composition of the sample is. We can measure its chemical makeup and obtain a chemical formula using the electron microprobe. And we can do that down to the micrometer scale. Then we have a transmission electron microscope that's capable of actually resolving atomic scale structure. So we can actually see the individual atoms within all kinds of materials. And so the transmission electron microscope is used to understand the atomic scale structure and long range atomic order in the sample. And so when we put all of that information together, what minerals are there, with what are they spatially related, mm-hmm. what are their textures, what are their compositions, what are their atomic scale structures, we can start piecing together the chemical pathways through which they form, the temperatures under which those reactions may have taken mm-hmm. place, and start to put together the history of the sample, and of course, by extension, asteroid Bennu itself.
Very good. Tom, this has been fascinating. I really want to thank you for coming on today.
Yeah, it's been great. I love talking science. I love right. talking about the mission, and I'm happy to chat with folks like yourself who are super interested and eager to learn about it. So thanks very much.
All right. Thank you. Well, that'll do it for this episode of the Observer's Notebook podcast. Again, I want to thank Tom Zega from Arizona State University and the OSIRIS-REx mission for coming on the podcast today. I hope you all enjoyed it. We upload a new episode of the Observer's Notebook every few weeks. You can subscribe to us on iTunes. If you do, please give us a rating and a review. I'd really appreciate it. You can now listen on Apple Radio, iHeartRadio, SoundCloud, Spreaker, Google Play, Stitcher, Amazon Echo, Spotify, and the podcast is also available on the ALPO YouTube channel. You can help support the podcast by donating to it via Patreon, where you can give up to $35 a month, where you'll receive 1 year's membership to the ALPO and producer credits on the podcast. And with that, I'd like to thank the producer of this podcast, Steve Siedentop, and Michael Moyer for their continued generous support. A link for Patreon, as well as a link for the ALPO, is in the show notes. You can contact me via email at commentman@commentman.net or on Twitter at @ObserversNBpod. And until next time, my hope is you always have clear and steady skies. Thanks for listening.